Now we would like to do a few examples to demonstrate how we can solve a first order differential equation using Python libraries. And we will be using the SciPy package and import the solve initial value problem. That's the solve IVP library. We will be working with this package. And we also have some auxiliary packages like NumPy, and for plotting we have the matplot library here, pyplot. So these are the basic packages we might use in many different mathematical problems. So now what's the problem that we want to solve? Suppose we want to solve a first order differential equation given by dy dt equals to minus 0.5 times y. So you can change this equation to another first order ordinary differential equation, and you need to redefine our function. So first we need to define the function here, the right hand side of this problem. So on the left side we will just assume we have dy dt alone. So if you have a different problem, make sure you put this dy dt on the left side of the equation, and everything else on the right side of the equation should be the format. So that's what we are doing here. The right hand side of the equation is given, and as I said, you can always work out and do some algebra to let dy dt to be alone on the left side. So we put it like this, and that's my ODE function defined now. That is the right hand side of this ODE. And then we need to input the initial condition, and then we need to create a grid that we will solve this problem over a certain equally spaced grid points. And that will be for our t variable. So y of 0, let's say, suppose this is our initial condition. Again, you can change this to something else depending on your problem. This means at t equals to 0, y of t equals to 1. And then we define our t span. Basically, we are interested from t0, t equals to 0 and up to t equals to 10. So we consider this range as our domain that we are interested. And then we create the t-eval variable here that will be creating a linear span. Based on this interval, based on this open interval, we basically create 100 equally spaced grid partition. So we have a 100 partition here over the domain from 0 to 10. And then now we are ready to input all these into our solve IVP function. So the solve IVP, which is for the initial value problem, first we need to input what's the right hand side of this equation. We already defined it here. So that's my ODE, right hand side actually. And then I need to input what's the domain that I'm interested to solve this problem. And then I input the initial value. Again, you can have a different initial value, just update this. And then you need to input our grid points where this function will be evaluated. So once we input all these, then everything else will be done with this function, and it will produce us the solution. And then we can create a plot that will show the t values that we evaluate. We can evaluate our solution, and also we have the basically the value of the function evaluated at y of 0, and then we put some label and just create this plot. So if we see how does it look like, let me type it here. So this is od1 example.py. So if we run this code, basically we will see the output in this way. Basically, we can see we have this decaying solution for the problem dy over dt equals to minus 0.5 times y. And the initial condition is y of 0 equals to 1. And that is satisfied, as you see, y of 0 at time equals to 0. The y value equals to 1, as we can see in the graph. Now, let's look at our second example. And here it's pretty much similar like the first example, but we have a different differential equation. As we see, we need to leave dy dt term on the left side of the equation alone, and then put everything on the right hand side of the equation. And suppose in this problem we have 2 minus 0.1 times y. So we can, just as we did in the previous example, we can define the ODE now with constant. So we call this just a different function name, but you can give any name you want. Just be consistent to call this, to input the same name for the IVP function here. So we define the right hand side, and then as usual we need to define what's the initial condition for this problem, and then we need to define what's the domain that we are interested to solve this ODE, the ordinary differential equation. And then we set up our grid points. This time, let's say we want to have 200 partitions of this domain from 0 to 50. So we created this. And then finally, we call our function with the ODE with constant. That's the right-hand side problem. And then we have the interval we are interested, the initial condition, and the grid points where we will evaluate the function. And then as you see, we can print the solution, and we can also create a plot to see how does the solution looks like. So let's run it and then see the output. So as we can see here, this time the solution for dy dt equals to 2 minus 0.1 times y, y of 0 equals to 0. And the initial condition this time was y of 0, so the value at t equals to 0, that's 0. That is satisfied, and it must be satisfied, of course. And for the range of values from 0 to 50, as you see, we have evaluated this function at actually 200 points. So as you can see here, this is the printed statement for the solution. So as you see, the y values are here. So we have actually quite many y values here because we have partitioned this domain into 200 pieces. Okay, so in total we have 201 points on this grid that we created. So thank you for watching. See you next time.